This is section 3.5a, Exponential and Logarithmic Models. These are two graphs of the exponential growth and decay models. And as you can see, they have the basic shape of exponential functions. A is the initial amount. B is the rate constant. And t is the time. Sometimes it's in seconds, sometimes days, sometimes years. But exponential growth and exponential decay occur frequently in nature. And it's because when something grows exponentially, it grows slowly at first and then very quickly. When something decays exponentially, it decays quickly at first and then quite slowly. Now, if we look, for example, at the graph on the left, representing exponential growth, for the t-axis, the time axis, obviously the negative numbers don't mean anything on this graph because there's no such thing as a negative time. But at time 0, if the initial amount is 1, well then it'll cross the y-axis at 1. And then as time goes by, we can see that growth is rapid at first, and then gets even more rapid as the time goes on. Turning now to the graph on the right, exponential decay. Again, the negative times have no meaning. The only reason they're on these graphs is just to show how the curve is taken from the exponential curve. But if we look now on the positive axis, the t-axis of the exponential decay curve, we can see that at time 0 we still have the initial amount, but as the time goes on, the amount goes down and down, initially quickly and then more slowly later on. So this is just a general introduction to exponential growth and decay. These are models, and what that means is that they represent real-life phenomena and real-life data. An example you've already seen is A equals PE to the RT. Remember when we were doing compound interest? Well, that was the formula for compound interest when the compounding happens continuously. And as we can see here, it fits in perfectly with the exponential growth model. A is the final amount. P is the initial amount, or in this case, little a is what represents it on the model. E is E, of course, and then R is the rate constant, and T is time. So we can see that A equals PE to the RT is simply an example of the exponential growth model. So make sure that you copy down these graphs and whatever data is written, because you'll need to refer to this later. Let's talk first about exponential growth. The model y equals AE to the BT. Once again, A is the initial amount, B is the rate constant, and T is time. So this is our table of data. On the left column we have the year, 2000, 2001, 2002, 2003, 2004. And on the right column we have D, which is the number of houses with digital TV. So in the year 2000 there were 30.92 million houses with digital TV. And going down the table we can see that the amount increased. And it actually increased exponentially. So the equation that models this data is D equals 30.92 e to the 0.1171 t. Now, the 30.92, we can see where they get that number. simply our initial amount, since we're starting the model in the year 2000. So that's our initial amount. And the B is 0.1171. That actually was calculated from the data. There's no particular reason why it has to be 0.1171. That is simply the B that was calculated from the data. Okay, so if T equals 0 represents the year 2000, in what year will the number of houses with digital TV reach 210 million? So pause the video, try to set up an equation, and then resume when you have an equation set up. Okay, so you should have written down your formula. This is your exponential growth model for this particular set of data. And then you put in 210 as your final amount, because that's what the question asks. And from there, you simply need to calculate T. And you can do that really just on your calculator. So first you divide both sides by 30.92, and then you go from there. Now, if you don't already have an answer for T, this is a good time to pause, get an answer, and then resume the video when you do have an answer for T. So continuing now, we just take the ln of both sides, because we want to get the variable by itself, get rid of the e. And we end up with ln 210 over 30.92 equals 0.1171t. Divide both sides by 0.1171. And we end up with 16.36 equals t. Now remember that t equals 0 represents the year 2000. So you should be able to tell me what year is represented by 16.36. And yes, that is the year 2016. The number of houses with digital TV will reach 210 million. Let's look at another example of exponential growth. Y equals ae to the bt. In a colony of fruit flies, there are 100 flies after 2 days and 300 flies after 4 days. How many will there be after 5 days? Okay, so this is an exponential growth problem because the flies reproduce exponentially in the same way that, for example, bacteria reproduce exponentially when they have an unlimited food supply. Okay, so let's translate the English into math. We can set up one equation where we have 100 equals ae to the 2b. We don't know what a is, the initial number of flies, but we can fill in what we do know. We know that there are 100 after 2 days, so 100 equals ae to the 2b. And the other equation we can set up by translating English into math is 300 equals ae to the 4b. Because we know that there are 300 flies after 4 days. Now, the question is asking us for how many there will be after 5 days. And in order to solve it, I'm going to need to find b, the rate constant. Now, there is actually a way to solve this without a, as we're going to see. So we don't know a or b, but we know that the amount of flies increased to 300 in the last 2 days. That is days 3 and 4. Also, the starting amount at the end of day 2, that is after 2 days had elapsed, was 100. Okay, so without even knowing the a of day 0, we can work with what we are given in the following way. Okay, so look at equation number 2 again. 300 equals AE to the 4B. And let's rewrite that as 300 equals AE to the 2B times E to the 2B. Now, you'll probably remember from Algebra 2 that when we multiply numbers that are being raised to an exponent, and we have the same number, well, we simply add the exponents. So e to the 2b times e to the 2b is the same as e to the 4b. Okay, so I simply rewrote equation number 2. Okay, now looking at 300 equals ae to the 2b times e to the 2b. That is the equation I just put up on the screen. Looking at that, we can notice something. ae to the 2b. Well, that was already defined in equation 1. Equation 1 is 100 equals ae to the 2b. So we know that ae to the 2b equals 100, and therefore we can substitute it and simply put that into our equation now. So we have 300 equals 100e to the 2b. Now it looks like we can get b by itself. So pause the video, calculate b, and then resume when you have it calculated. So proceeding now, divide both sides by 100. We get 3 equals e to the 2b. Take the ln of both sides. ln3 equals ln e to the 2b. ln3 equals 2b. And ln3 divided by 2 equals b. Alright, so that's our b. Now, it's usually better not to calculate it and get a big number with many decimal places because it's kind of a hassle to write all those digits. Or the other temptation is to simply round off too early, but that'll make your final answer inaccurate. So let's just leave it as ln3 divided by 2. That's our b. Alright, now that we found b, we need to try to find the final amount, because that is what the problem asks us for, the final amount after 5 days. Alright, so we're going to use this equation. Y equals ae to the 5b. We put 5 in for t because it's 5 days. We want to know what y is, the final amount. And once again, we don't actually need to know a. There's a way we can solve for t, solve for y without even finding a. So let me show you that. We can rewrite it as y equals ae to the 4b times e to the b. Again, we have to add the exponents, so we can see that it's really the same. It's just e to the 5b, because 4b plus b is 5b. And once we have it written this way, you're going to notice something familiar from equation 2 above. Equation 2, 300 equals ae to the 4b. And therefore we can substitute that 300 in. And we'll see this. Y equals 300 e to the b. Okay, we just substituted 300 in from equation 2. Okay, and at this point, you should be able to calculate y. So pause the video, calculate y, and then resume when you have an answer. Continuing then, you should plug in ln3 over 2 for b, and you get 519.62, 520 fruit flies. Notice that the correct answer is 520 because you can't have 0.62 of a fruit fly. I mean, you can. That's kind of gross. You know, cut a fly in half. But obviously, when flies reproduce, you never end up with 0.62 of a fly. So when you have problems like this, you have to use your common sense a little bit and think of what's a logical answer. So 520 fruit flies is the best answer. Now let's talk about exponential decay. Y equals ae to the negative bt. This is a formula that you've seen in a previous lesson. It's the formula for radiocarbon dating. Alright, so R is the ratio of carbon-14 to carbon-12 at time t after an organism's death. Okay, so just a quick review on that. You might remember from biology that in living beings, the, of course, most abundant carbon isotope is carbon-12, which is the normal carbon isotope. But carbon-14 is the radioactive, naturally occurring radioactive carbon isotope. And all living things have a small portion of C14 in them. But once an organism dies, whether it's a plant or an animal, that radioactive carbon-14 begins to decay. And what that means is it simply changes from C14 to C12 by losing 2 neutrons. Okay, well, you don't need to worry about that background so much for this problem, but that's where this comes from. R is the ratio of C14 to C12 at time t after organism's death. So our problem is a monkey fossil is found with R of 1 over 10 to the 13th. How old is it? Pause the video and try to do this on your own, and then resume when you have an answer for t. Alright, so you should have set it up like this. 1 over 10 to the 13th equals 1 over 10 to the 12th times e to the negative 1 over 8223t. And then it's just a matter of getting t by itself and solving, as we have in previous lessons. And you should have ended up with t equals 18,934.16. Now, again, we have to use our common sense, kind of like we did with the fruit fly problem. And what I mean in this case is that radiocarbon dating never tries or claims to be accurate to the year, but rather to the closest several hundred or 1,000 years. So you should write your answer to the nearest 1,000 years, and the monkey fossil was about 19,000 years old. Here's another example of exponential decay. At Chernobyl in 1986, there was a huge tragedy. It completely destroyed the city, and even today, that city is uninhabited. So 10 pounds of overheated plutonium caused a reactor meltdown that destroyed and contaminated the whole city. If the half-life of plutonium is 24,100 years, how much plutonium was still in the Chernobyl reactor in 2010? Okay, so a little bit of background on half-life. You probably have heard of that before. Half-life of a radioactive element is simply, no matter what your starting amount is, it could be 10 grams, 10 pounds, 10 tons, whatever. The half-life means that after that amount of years, you're going to have half of your original amount. Okay, so for example, here we have 10 pounds. That's what we started with in 1986. The half-life means that after 24,100 years, there will be exactly half of what we started with, which is 5 pounds, half of 10. Okay, so this is a problem that you're going to need to do in 2 steps. First, you're going to use the half-life to calculate B. Then you'll use the B that you found to find the final amount, or Y. Okay, so let me show the model here. The model is Y equals ae to the negative bt. This is our model for radioactive decay. And now, pause the video, try to do this on your own. Remember, it's in 2 steps. First, use the half-life to get B, and then, once you get B, try to find Y. Okay, so pause the video, try to do this on your own. If you get stuck, it's okay. It's normal. You can just resume if you get stuck. Alright, so our first step is to try to find B using the half-life. We can set it up like this. Remembering what a half-life is, the fact that after that amount of time you'll end up with half of your original amount. Well, our original amount is 10. That's why I put 10 in for A. And after 24,100 years, there will be half of that original amount left. That's why I put 1/2 10 on the left side of the equation. Well, as you can quickly see, the 10s cancel. And I end up with 1/2 equals e to the negative b times 24,100. And you can easily get b from that. ln 1/2 equals ln e to the negative b 24,100. ln 1/2 equals negative b 24,100. ln 1/2 divided by negative 24,100 equals b. And we can stay with that instead of writing a number with a lot of decimal places, because in the end, this is actually going to be faster. Alright, so now that we found B, we need to try to find Y. So we're going to use the radioactive, or the exponential decay or radioactive decay model again. Y equals ae to the negative bt. Y equals ae to the negative bt. Now, we found B, so we can put that in. And we also know T from the problem, because the starting year was 1986, and the finishing year is 2010. And that means 24 years has gone by. So here's what we put into the model. Y equals 10, that's our initial amount, times e to the negative b, that whole thing, ln 1/2 divided by negative 24,100, times my t, which is 24 years between 1986 and 2010. Okay, so you should have ended up with this equation. And then from there, we can easily just use our calculator to evaluate this expression. And we end up with Y equals 9.993 pounds. That's how much of the original 10 pounds of plutonium is still left in Chernobyl. And you can tell by looking at that number that it's really not much less than 10, which means that, it's going to take a long time for that city to be uncontaminated. Here's the classwork. Page 265. Please write down these numbers. For number 41, pay attention to the note in parentheses. Use the formula from the carbon-14 example. That's the one that we did on the monkey fossil. You can use that formula from your notes for problem 41. And as usual, we'll have time to work on this in class, but you can start on your own.